Okay, very good. Brendan, if you want to start to share your screen.
Oh, yes. Okay, here we go. Everybody can see my slides?
Yes, they look great. Okay, so we are very pleased to have Brandon Kriesten here with us today to give us a seminar on Quark and Gluon distributions in the nucleon, their spatial distributions as opposed to their momentum distributions. Brandon is a postdoc at the Center for Nuclear Femtography, and that's it. Thanks, Brandon.
Yeah, thank you. Thank you so much for having me. Like Jennifer said, I'm going to talk about Gluon and Quark and Gluon spatial distributions, in particular, how we access them through the GPDs. And I'm going to also talk a little phenomenology of GPDs and how we're planning on extracting them from exclusive experiments. All right, so here's a quick outline. So I'm going to talk a little bit about this overview of a program called femtography, kind of what that means. It's a buzzword, but I want to kind of demystify this buzzword a little bit for everybody. Give some theoretical motivation, talk about this GPD parameterization that was the subject of my thesis, and how we use it to create spatial images, but go beyond these images. And also talk a little bit about some GPD phenomenology and machine learning. So first, many people probably heard this before, femtography in the nucleon, creating images, particularly these kind of nice images that are that can be extracted, hopefully from data. And this is an example of what one would typically see. However, I think of femtography as moving beyond images. So I think of them as data-driven extractions of these sort of correlation functions, these quantum mechanical correlation functions that describe, in particular, the dynamics of the quarks and gluons inside the nucleon. And in order to do this, we have to use a variety of different deeply virtual scattering processes. So one of these processes, such as deeply virtual Compton scattering, is that these are unique opportunities for accessing and probing these quantum mechanical phase space distributions. As you can see here, the GPDs parameterize these distributions. And one could think, okay, why do we care about the nucleon in general? Well, we know that mass is a consequence of dynamics, in particular the dynamics of protons and neutrons. This is the subject of QCD in general. So it's critically important that one establishes a QCD framework that describes the physical properties of the nucleon and directly ties them to experimental observables. So this is, in essence, what I think of as the definition of femtography, and it's the motivation behind a lot of my work in trying to extract these sort of quantum mechanical phase space distributions. So giving some theoretical motivation a little bit, we know that when we want to describe the fundamental properties of the nucleon, we have to go to the QCD energy momentum tensor, which encodes information such as energy densities, momentum density, pressure forces, shear forces, things like these. And it was shown, for instance, by Shandong Ji in 1997, that one can parameterize this the QCD energy momentum tensor through these form factors when you take the matrix element between off forward proton states. So when you have these QCD energy momentum tensors sandwiched between proton states with different momentum, the difference parameterized by this momentum transfer delta, you can describe this in terms of these sort of gravitational form factors, these A, B, C, and C bar. And these matrix elements or form factors essentially describe the elastic scattering of a graviton off a proton. That's fantastic. But how do we access these sort of matrix elements in experiment? So we know that, for instance, the coupling of a graviton to a proton is extraordinarily small, probably not even measurable within the next century of experiments. So one has to think about ways that we can extract the information contained in these form factors through current experimental measurements. And why are these important? So for instance, if you take the spatial distribution R across the momentum components of the energy momentum tensor, giving this angular momentum tensor, you can then integrate that and describe angular momentum of quarks and gluons. And when you go through and use the gravitational form factors in this description, you see that angular momentum and the longitudinal angular momentum in terms of quarks and gluons is given by the form factors A and B that I showed before at zero momentum transfer. So this directly shows that information on the physical properties of the nucleon are contained in these gravitational form factors. And these gravitational form factors, for instance, can be calculated on the lattice. So this is a lattice calculation of these quantities, for instance. Now, what's important is that we have to be able to measure these gravitational form factors or the information contained in them in experiment. And this is the critical work in which one can show that there's a direct connection between moments of the GPDs that parameterize, for instance, exclusive scattering processes such as these, and the gravitational form factors. So for instance, the integral of the first melon moment of the GPD H gives you the gravitational form factor A plus the C form factor, and similarly for B. So GPDs represent a direct connection between the QCD energy momentum tensor and experimental observables from such exclusive processes. And now, so one can ask, what are these GPDs? And this, for instance, this is the correlation function of a GPD, in which you have quark operators at off-diagonal positions. You have your Wilson line that makes this object gauge invariant, and then you have your sort of projection operator of the quark fields. And all this is sandwiched in between proton states of different momentum. And you integrate out, for instance, the transverse momentum of the quarks. And so you can see that there's two sort of positions in this two sort of distances in these sort of Wigner distributions, one of which is the relative average transverse position from the center of momentum, this BT, which is Fourier conjugate to the distance, but which is Fourier conjugate to the momentum transfer between the initial and final proton in the transverse component of it. And then there's the part that we integrated out, which is the relative average transverse momentum, the KT dependence, which corresponds to this light cone distance CT.
Brandon, can I ask you a quick question?
Of course.
Is this BT the same variable as, for example, B perp that like the color transparency people are talking about?
Yes, so one can think of, for instance, B perp. So it depends. So this is not the let's see. This is, okay, so let me actually go back. Oh, wait, whoops, going the wrong way. Here we go. So B perp would be, for instance, a Fourier conjugate to the external momentum. So I think with the color transparency people, B perp is also called Z perp in our language. But I think the B perp that you're talking about is actually what we call Z perp.
Okay.
Yeah. I think that's the way to think about it. But there is, so this is, for instance, the transverse position between when the quark is struck by the initial state photon and when the quark emits the final state photon. So this is the correlation distance between that of that correlator in transverse position space. But B perp is the distance between the center of momentum of the quarks and yeah, it's the distance to the center of momentum of the quark system. Yeah.
Bren, that makes a lot of sense because their B perp is like the size of the point-like configuration if it goes point-like. So that makes sense. Thank you.
Right. Okay, so now in order to get really anywhere in seeing what the size of these objects and what the size of the observables are, it's always useful to have some sort of parameterization of GPDs. So I'm going to talk a little bit about the GPD parameterization that we've developed. I'm going to motivate it through the Quark sector, and then I'm going to just quickly flash how we use it for gluons. And then I'm going to talk a little bit about developing some spatial images and some things that we can do with this parameterization. So our parameterization is based off a spectator diquark model. And one can think about it if you take this amplitude, this scattering amplitude for instance, deeply virtual Compton scattering. You have, your initial and final state nucleon, you have your scalar diquark here, and you have your quark loops and your photons coming out. Now, one can ask, can we separate out, for instance, the QED piece, this sort of Compton scattering piece here, from the actual GPD itself? So when you write out, your Feynman rules for this whole thing, you get this object here, and it's not directly apparent that one can actually factorize, for instance, this separation between the purple and green pieces. So what we actually do is we can split these quark lines by looking at this object here, the k/+m, and we can see that it can be written in terms of leading contribution of a UU bar, and also a subleading term that's proportional to the off-shellness of the quark. Now I say this is subleading because you can see that it's a 1/k0 term here. So this is 1/p plus suppressed. And so this term, because I'm just calculating leading order GPDs, we kind of throw this away, and you're left with a UU bar, and this can be separated, right, into two contributions, one going to the top part and and a U bar going to the bottom part. And so what we can do is we can sort of separate this object into three pieces. One kind of vertex here, which is described like this, one vertex, the Compton scattering amplitude up here, which is your normal QED process, and then another initial state vertex. And this is all done through the language of helicity amplitudes. So we take into account the proton and quark helicities here. Now these vertex functions are interesting. You have a quark, diquark, and nucleon vertex. And that's a little tricky. So how do we model it? So what we do in this, in our case, is we actually use a dipole form factor for this vertex. And what this allows us to do is it actually introduces a new variable, a transverse momentum cutoff parameter that we call m lambda. And this is the threshold mass of the spectator. So this allows us to introduce more flexibility in our model. And so what we can do is you can see that we've split this into vertex functions. And so we can overlap these vertex functions to create what are called helicity amplitudes, which describe, for instance, the helicities of the initial and final state protons and quarks. And so with these certain contributions of longitudinal helicity, so plus, 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 you take the overlap of your calculation of vertex functions, you get something that looks like this. And you can construct the GPDs themselves, let's say H, for instance, by summing over all the helicities. So for instance, H is the unpolarized GPD. And when we sum over all the helicities, we just take our parameterization and sum everything up. Similarly for E is also of interest in that E describes a transversely polarized proton with an unpolarized quark. And so you can see that these are transversely polarized because the proton helicity flips between initial and final state. And this is what our calculation looks like. It's not too crazy, but we have, for instance, all these mass parameters that come in. So we have quark mass, this threshold mass that's introduced through this vertex function, and also a spectator mass that we introduce as well by putting the spectator on shell. And so these all are introduced in order to parameterize and fit our model and increase the flexibility. Now, we also, it should be noted that, the spectator diquark model, the scalar diquark model doesn't actually produce the correct low X behavior PDFs on its own. This has been known for actually quite a while. And so what we do is we have this sort of reggeization procedure in which we allow the spectator mass to vary, and we give it a distribution. And when you integrate over that spectral function, what you actually see coming out of the GPD is this x to the minus alpha just kind of pops right out there. So this is actually, and like I said, this has been known. This paper is by Brodsky et al. And then we also have this extra term, this t-dependent piece that is sort of related to these Regge slopes. And what this does is it allows us to control the size of the proton through Fourier transform at large transverse distances. So this makes sure that our proton isn't, constantly increasing or non-zero out at large transverse distances. It gives it a finite size. And our final GPD calculations, for instance, look something like this. So we have the spectator piece that I showed you before with the mass parameters, normalization, constants, etc., and also these reggeization terms. And so there's 8 total parameters per GPD flavor, per GPD and per flavor. So to parameterize all the GPDs that enter into DVCS, there's a lot of parameters that are fitted, but this allows for flexibility from fitting to different channels of different channels of experiments. Now, we only actually parameterize, for instance, the DGLAP region, which is x greater than c for the GPD. And what we do is the region between 0 and c in x is called the ERBL region. And what we do is, instead of going through and reparameterizing our model, we actually come up with this kind of clever way in order to model this part, in that we know, for instance, that the ERBL region is controlled through symmetries. So, for instance, the Gluon PDF, let's take the Gluon PDF. We know that the Gluon PDF, because the Gluon is its own antiquark, is its own antiparticle, that it has a symmetry about x equals 0. This sort of symmetry translates into this ERBL regions as a symmetry as well. And so, for instance, the valence quarks, we know it has the exact same, it has the same symmetries as well. And this is how we construct our ERBL region, is this way, rather than recalculating different diagrams. And so our GPD model kind of has all these sort of essentials that one would expect. It obeys parton model symmetries. It obeys positivity constraints, which say that at finite t, that it is actually smaller than, for instance, the PDF in this region. It obeys polynomiality at the numerical level, and it's also it can also be perturbatively evolved using a QCD, a PQCD numerical framework. So we developed this kind of evolution code that allows us to evolve our GPDs, and you can see that it just we can do this pretty simply, and it directly enters into this. So we can evolve our GPDs up to the scale of the data and make actual predictions on observables. So one can look at, for instance, the GPD H and its polynomiality. So you know that if you take the integral of Mellin moments of H, you can write it in terms of these gravitational form factors that I showed before. So for instance, the 0th moment of H is actually just the form factor A10, which is just F1, you know that the first moment is these A20 and C20, which directly tie into those gravitational form factors I showed previously. And then also there's the third moment, which are higher moments that can be calculated on the lattice. And so what we do is we compare these moments to these lattice QCD calculations, and we show that within error bars, we're consistent with the lattice moments. So this is how we determine that our parameterization obeys polynomiality, for instance. And one could do something similar with E as well. So here's kind of this flash picture of what we do for the gluons now, and that this exact same procedure for the quark distributions can be done with the gluons, except keeping in mind now that your spectator is no longer a scalar diquark, but it's actually a color octet gluon. And so your parameterization, your vertex functions change a little bit. You have your epsilons now instead of your U bars. And but all in all, the exact same procedure holds in that the calculation of the GPDs is pretty much the exact same. I mean, we don't have a quark mass anymore, so we have one less parameter. But this is in essence what the gluon GPD H looks like. So there's 7 fitted gluon parameters, and we also fit the initial scale for perturbative evolution. And so this is what these kind of things look like. For instance, this is our gluon PDF. It evolved from an initial, this is what it looks like, the initial scale, and then we evolve it to a final scale 4. And similarly for the gluon GPDE, which I'll describe in a little bit, this is actually a novel work in that the gluon GPDE has not necessarily been parameterized. It's been modeled, but not necessarily parameterized before to lattice data. So this is where kind of the synergy between theory and lattice come in that we take our gluon GPD and fit it to the lattice QCD calculated moments. So this is kind of all we really know about the gluon T dependence is through the lattice calculations. So for instance, in this Detmold and Shanahan paper from 2019, they give us the data for the gluon calculated moments at a specific pion mass. And so we can then fit our parameterization parameters to these T dependence of these gravitational form factors. And so this is what our gluon GPD looks like, for instance, at various T as a function of X. And so this is for the gluon GPDH. And now even more so interesting is the gluon GPDE. So the Detmold and Shanahan paper actually calculate the moments of B, this B, G, gravitational form factor. However, they tell us that this gravitational form factor is consistent with 0. But you know, in order to get anywhere with this gluon GPD, what we did was we refit the data to a dipole fit instead of just assuming a constant or 0. And we parameter, so that's how we parameterized our GPD. Now, the interesting part about this is that these data have massive error bars, for instance, and they're kind of jumping all over the place. So there's a lot of flexibility in this fit, and there's a lot of interesting thought that can go into, for instance, how this gluon GPDE can be, the T dependence can be fitted.
Then, could I ask you what is the dipole like for the gluon GPD? What the dipole is between what and what?
Oh, so we just assume this sort of form, this sort of dipole form of the so this functional form, for instance,
okay,
is what it's fitted to. So we just so what we do is we fit the lattice. So the lattice data here is fitted to this form, alpha over 1 minus t over m squared. And so they determine the parameters alpha and m from this from here. And then so we do a similar thing for this form factor. And then once we fit that data, we then work to make we then fit our GPD to that fit, for instance.
Good.
So what one has once you develop the Gluon GPDs, and a similar game can be played for the antiquarks, is that you can develop this kind of full exclusive picture. So you go from forward objects, the PDFs, the parameterization with the PDFs, to now a fully off forward picture of these distributions. So you have U valence, D valence, the C quark distributions, and the gluons. And so this is what we show here, and going from PDFs to GPDs, how this picture sort of changes. And when you have this, the full power of this parameterization is that one can start making predictions for, let's say, the EIC cross sections. What one would see for DVCS cross sections at the EIC. And so you can see that we show some sort of preliminary plots of, what the DVCS cross section will look like as a function of the center of mass energy. And now this can only really be done because we've added in this quark and this gluon and anti-quark distribution. Now, moving on to this sort of transverse position space picture, one can define, for instance, the probability density of finding a parton at transverse position from the center of momentum as a function of the parton and proton polarizations. So this looks something like this, in that the probability density is given as an unpolarized contribution, a transverse momentum shift, and then also this is the probability density for a longitudinally polarized quark instead of a longitudinally polarized nucleon. And this is the Fourier transform of H tilde, for instance. And so one can see that there's these sort of transverse. This has been well known by this work by Matthias Burkhardt, and that there's these transverse polarization shifts in the unpolarized distributions that are proportional to this GPDE. So we started kind of looking at these objects and what under Fourier transform, what we could do with our parameterization. So these are just some toy plots that we did of that are similar to what I showed in the very first slide, but these are using our parameterization. Now these are Fourier transformed, and these are done at the initial scale. But there is a evolution framework that can take these pictures and actually evolve them to the final scale as well. It's just that this was not done for these plots. But yeah, so these sort of pictures one can use and start to develop some phenomenology with, and start to play around with what exactly do we get from these images. So one such thing is we can talk about radii, for instance. So if you take the expectation value of this BT that I showed you before and defined before, you can do this as a function of X for various different flavors of quarks and also the gluons. So you can see what I'm showing here is what the quark radii look like as a function of X as they go to low X. This is in femtometers. And also the gluon distribution. As you can see, it goes right up to it pretty much goes right to the expected value from recent experimental measurements, around 0.6 centimeters. So this is all good. This means that everything's really consistent in these pictures. And these are things that we're starting to look at, is moving beyond, for instance, these images, which are nice, but they don't give you very much information. But one can use these images to start to describe actual physical properties, such as radii. And so this is kind of the important step of femtography, is understanding how we go from this picture to this picture. All right, now I'm going to talk a little bit about some explorative ideas we've had in terms of GPD phenomenology, and also the utilization of machine learning and artificial intelligence. So I described, for instance, before this GPD virtual Compton scattering process, which is lepton-proton scattering into a final state of lepton-proton and real photon. And now this is a really complicated process. You have a lot of particles in the final state. And so there's quite a few amplitudes that go into this scattering process. And what this means is that this is kind of a rich but yet complex structure that encodes the physical properties of the nucleon. And so this was first developed, for instance, by Xiongdong in '97. And recently we wrote a paper in which we define all of these amplitudes in terms of the helicity amplitude formalism, and we calculate all their cross sections. So for instance, the main ones that the main amplitudes that I'm going to talk about today are this as the DVCS process, which directly encodes information from GPDs, but also this background QED process called Bethe-Heitler, in which you can see you have initial lepton-proton, but in the final state, you also have lepton-proton and final state photon. But this is all only parameterizing the elastic form factors. So this is purely radiative background that one needs to keep in mind when doing this calculation of the cross-section. And now, as you can see, because I'm calculating cross-sections, you have to do amplitudes, the sum of the amplitudes squared. And so not only do you get cross-sections for DVCS and Bethe-Heitler, but you also get interference terms between these two. And these are going to become really important when we discuss some phenomenology here. And this is, for instance, what the kinematic scattering planes look like. You have a lepton plane in which the lepton scattering process happens, and you have a hadronic plane, this orange plane, in which the hadron, the final state hadron gets emitted out of. And so these two kinematic planes allow one to define this azimuthal angle phi, which is critical to extracting for information from cross sections. And so you can write the DVCS cross-section in a very nice way. It's very reminiscent of, for instance, TMDs, in which you can identify all the various contributions at leading twist and subleading twist, and even further suppressed by the Q-squared. And also you can identify, for instance, parity violating pieces that should be zero, so we don't consider them. And also one can then write out, so that's the DVCS cross-section, pretty simple. One can also write out the Bethe-Heitler process, and it is extraordinarily simple. So you can see that it takes on this form in which you have F1 squared plus tau F2 squared. This is kind of like the GE component in elastic scattering. And also here's the tau GM squared with various kinematic coefficients in front of them. And so these two terms come with exactly calculable coefficients. And you can see that there's actually no need for a sort of harmonic expansion of these cross sections. Everything's exactly calculable. And it's actually really simple to code in terms of Monte Carlos, this thing's like 2 lines. So calculating things in this way can be very beneficial rather than doing some harmonic expansions, which are common in other formalism. And you can, when you write out the interference cross-section, you actually start to see that the very similar structures start to emerge. So F1H plus tau F2E, this is almost identical, if you take the forward limit here, to the F1 squared plus tau F2 squared term that I showed you before. So this is starting to look a lot like the elastic scattering cross-section. This is like a GM squared term. Now the difference is that because of the presence of the DVCS amplitude and the fact that you have 2 independent photons, you get you get a sensitivity to the axial charge here, which is given by this H tilde term. And so what I show, for instance, here is a calculation of a fit to the cross-sectional data. and also how our formalism, which I call this VA, differs from other formalism in the literature. So, you know, we've done these studies, and if you're interested, you can look at these papers here. But the main point is that using exactly calculable coefficients makes your life a lot easier, and it makes things actually easier to fit as well. So we came up with this idea of utilizing an older technique of Rosenbluth separations and making these kind of Rosenbluth-like separations, in which what we do is we numerically studied all these coefficients that are in front of these terms, and we saw that this term, for instance, that's sensitive to axial charge, is not particularly large. And this makes sense if you think about elastic scattering. Your axial component of the elastic scattering cross section is not going to be very large, probably. So this is very reminiscent of that fact. And so what happens is when you get rid of this term, you start to see that you can develop a linear relation if you plot the interference cross section versus these coefficients that are exactly calculable. And so you can make these sort of linear relations that are nice to fit, and you can actually, using just one equation, one observable, extract two unknowns. So this is for the first time our ability to extract, for instance, the GPD, the Compton form factor, real E, from unpolarized experimental data. And so I show, for instance, what this looks like for real H. And now the tricky part here is that all these Compton form factor extractions, I compare them to other methods, both neural network methods and some using standard statistical analysis methods. But they all use the same data, but because everybody uses different extraction methods and different cross-section formula, what you end up is you can extract different values, central values, and more importantly, different sized error bars. So this is something that is tricky when doing phenomenology, is that it represents a need for this sort of benchmarking techniques for these extraction methods. And as you can see, all these methods can just sit right on top of the data, so that's kind of concerning. It also kind of raises this question of how much information are we actually getting from these Compton form factors and being able to fit to the data. So that's interesting questions. And of course, one can ask, where's the glue? So one can think of using a lever arm at the EIC to extract through perturbative evolution the gluon distribution from scaling violations in these DVCS structure functions. So this is something that's also interesting to think about as well, because you can see the gluon distribution directly enters these DGLAP evolution equations. So, or the Gauss-Rayleigh-Parisi equation. So one can think about, also looking at these as well for extracting gluon distributions. Now, all of this should sort of point to the fact that there needs to be a new standard of analysis and processing this data. And one of the techniques that's dear to me is machine learning. And one of the things that I would like to emphasize is that machine learning is more than more than necessary for these sort of analyses. And it's so what is machine learning? It's the subset of a larger category called artificial intelligence. So first of all, these things aren't actually in the literature. They're often tossed back and forth as being the same thing, but they're actually different in that machine learning is actually a subset of artificial intelligence techniques, and that machine learning utilizes the statistical techniques to train the machines and improve them and learn how to perform a task given a large set of experiences. So what this automatically tells you that machine learning is not a black box technique. It's actually a statistically rigorous process. So this is something that I think is beneficial to develop in this sort of femtography framework, and that I think of machine learning as a computational framework for cryptography. So it's essential to establish machine learning techniques to study and analyze DVCS data. And what this allows us to do is establish a common language between nuclear theory, nuclear phenomenology, and machine learning. And so what this will do is create a further framework for synergistic studies. And so I see us developing, for instance, machine learning techniques that will take us from data all the way to physical properties that we can extract. So we've done a little bit of this study so far, and that we've looked at the utilization of deep neural networks to study extrapolation, generalizing the information learned on DVCS data to kinematic regions beyond the extent of the data. So what I show here, for instance, is a supervised network that's trained on data that's located here. And then we test what happens when we extrapolate to regions where the data isn't. And we can see, for instance, that there is information learned in the range of the current data that can then be generalized to kinematic regions outside of the data. So this is important. This is essentially telling us that we can squeeze way more information by taking this global perspective and studying these trends in the data. We can squeeze more information out of the data than just the data points that are given. So this is important, and we talk about this in terms of physics-informed neural networks, which I'll talk about a little bit. Now, one can also think about machine learning as a way to ensemble all the information that we have from nuclear physics. So not only studying data, but incorporating data from other sources besides just experiment. One could include, for instance, lattice QCD calculations, theory constraints, all that swirled into one sort of machine learning pipeline in order to extract, for instance, the GPDs from data. So we took a first step towards understanding this by doing a supervised extraction of Compton form factors from the data. So we know, for instance, that there are 8 beam and target helicity combinations allowed by experiment through parity, and that there are also 8 leading twist, chiral, even Compton form factors. Now, so that what does that mean? There's 8 unknowns and 8 equations. This should be a solvable system, right? Well, that's if all of these experiments overlap in the exact same kinematic regions and also have controllable error bars. And the likelihood of that happening with the amount of data that one would need is pretty slim. So we need to ask ourselves the question, how much information can we extract from single polarization observables? And this is what we did. So for instance, we took the unpolarized cross-section and we tested using a neural network, what is the values of real H that one could extract from this kind of global perspective. And so that's what I show here, for instance, as compared to the Rosenbluth extraction method that I showed before. And one can see that, for instance, the neural network is learning very similar information as the Rosenbluth extraction, and that these central values all are lining up. The error bars are pretty controllable as well. And what we did was we also looked at ensembling, for instance, 6 GB and 12 GB data, so that we can get a look at how the Q-squared development goes in this Compton form factor as well. So these are all interesting things, the extractions, and they're still in progress. I am not going to talk about this too much in depth, but the idea is that when the question I most often get asked when using machine learning is, well, how do you know what the error bar is? Is machine learning adding in some sort of error, or how do you know how you're propagating error, and is this correct? So this is something in machine learning that we call uncertainty quantification. And essentially what it does is it allows us to discuss the separation of reducible errors from that are systematic to the network versus irreducible errors that are inherent to the data. And so this is also something that we're looking at. We have our way to do it that is reminiscent of the replica method, but it's not necessarily the exact same. It provides, an alternate way of understanding error, utilizing what we call dropout in neural networks. And finally, with neural networks, we have this opportunity to utilize new sort of configurations to solve what are called inverse problems. And that if we have a Compton form factor, can we reconstruct the lost information of the GPD that's lost from integrating over this X variable, for instance? So can we reconstruct the GPD from these Compton form factors? What information is contained here that we can reconstruct here? And with what accuracy? So this is a sort of neural network architecture that we plan to use, which is a semi-supervised generative algorithm that recursively applies, for instance, theoretical constraints, a combination of theoretical constraints, experimental data, lattice QCD, calculated moments, in order to point by point reconstruct the GPD. And what this does is this is actually very similar to, this is using the technology of natural language processing, in which, for instance, machines learn how to construct sentences by sequences of words. So this is this is a very, still in the works, but this is something that we're looking at in solving these sort of inverse problems. So finally, I come to my conclusions. Femtography, as I described it before, because it's this data-driven framework, and it involves all of these sort of aspects from theory, phenomenology, machine learning, model parameterizations. So, and because it uses all these different types of exclusive processes to place constraints, it's a really complicated and difficult framework in order to develop. Now, some of these steps in this framework are well defined. For instance, going from cross sections to Compton form factor extractions. This is not, for instance, an inverse problem. It's a well-defined problem, even though it is difficult. But some of these steps aren't. We don't even really know how we're going to perform that step. So, for instance, from extracting GPDs from the Compton form factors, this sort of inverse problem solving. And so it requires a lot of exploration using a variety of different data analysis tools and moving beyond kind of the standard applications of statistical analysis that we're used to. And so creating these femtographic images are going to require just coalitions of different experts, experimentalists, theorists, data scientists, machine learning experts, lattice QCD specialists, and also visualization experts to work together to achieve, to extracting information. So thank you.
Excellent. Thank you very much. Brendan, I mean, how difficult is it for that very last point? How difficult is it for people to become, like for a pheno person, become also an expert in machine learning?
Yeah, I think that's a good question, in that one has, you almost have to be kind of like a hybrid person, in that you have to understand both in order to connect, the hardcore theorists and pheno people to the hardcore machine learning people. So we need those people that are in the middle that can speak both languages a little bit to connect these two types of people. This is something that I've been working on. It is difficult because I'm not a machine learning expert. I'm also not, hardcore into the theory of as well, so I'm kind of in between. And this is important because it creates this commonality, this language that both people can speak.
Yes.
But yeah, these collaborations where you're trying to connect these two fields are very difficult to handle sometimes.
Yeah, the bridge people are super important. I agree. That's good. Zhongling, do you have a question?
Just one basic question. So could you please explain more about the reggeized modification factor R, and why you add that factor, and based on what model, and why does it related to the proton size?
Yes.
The modification of the size. Yeah, I don't get that. Yeah.
Was that slide 35, Brandon, or was it
very early, I guess, maybe 25, yeah.
Let's see. I think here. Yeah. So this sort of reggeization term, it has sort of these two different pieces, right? This x to the minus alpha comes right out of the model if one allows the diquark mass to not be a delta function at mx, for instance, at the mass parameter, but rather have the spectral distribution. And what happens is when you take a certain spectral distribution and multiply it by the diquark calculation here, and you integrate over the mass of mx that appears here, what you actually end up finding is that this x to the minus alpha pops right out. And so this was shown by, for instance, Brodsky in these early, spectator models that Brodsky developed a while ago. And now this t-dependent piece is interesting in that, so because of the t-dependence here, when you take c equals 0, this is directly delta perp. And so this form is of the reggeization piece, because it has this delta perp in here. When you under Fourier transform, it allows this term to control the size in BT. So because of this this fall off at large t, because of the form here. So at large t, so at large delta t, or Fourier transform large bt, it's going to fall off much faster than just this term, this calculation does. Maybe that makes sense.
Oh, okay, yeah, it makes sense. It's just constrain the region. Okay.
Exactly, and it's actually really sensitive to for instance, this exponential, this p here.
Okay, so this just motivated by some model, right? Okay.
Right.
Okay, thank you.
And the Farid, please.
Hi, Brandon. In one slide, I think it's slide 31, you showed the off-forward and the forward distributions. Yes, this slide. And it's very interesting and intriguing to me what is shown on the right. The fact that the Gluon distribution kind of plateaus as a function of x, while on the left, right, it increases significantly. Do you understand what's the physics? Could you comment on these features?
Yes, no, that's a very good point. And so how we calculate, for instance, this ERBL region. So here at this point, zeta equals 0.2 is x below that and above greater than 0 but below 0.2 is called the ERBL region. And how we model this is through these through the partons model symmetries. So for instance, the gluon distribution, we know at x equals 0 has to be symmetric for x greater than 0 and x less than 0. So x equals 0 is the symmetry point of the gluon distribution. But how this translates in terms of GPDs is that at this x equals zeta divided by 2, or at 0.1, it is the symmetry constraint. So that's why what happens is it doesn't go up like it does for the PDF, is because we know that x equals zeta here has to be equal to x equals 0. So let me see if I have a backup slide here. This might be easier. I may have put this in. Yes, okay. Yeah, okay. So this is the valence quarks, but because the valence quarks and gluons have these same symmetries, you can just replace the argument that I'm about to say with these equations. So this is how we model, for instance, the ERBL region for the gluons, in that we have an x squared term, an x, and then a constant piece, because we know it has to be symmetric about x equals zeta halves, which is little x equals 0, for instance. And so this is why, as you can see here, the GPD for this red curve would be the gluon GPD, would be why it would go to the same point, why it doesn't blow up, is because it's constrained by symmetry to be the exact same point at this crossing symmetry point. Maybe that makes sense. Let me.
I have to think about it, but thanks for the answer.
Yes, yeah. So the short answer is that the point at x equals 0, this capital X equals 0, is constrained to be the same as x equals zeta, or little x equals c.
I see. Okay.
Symmetry. Yeah.
Thank you, Brandon.
Brandon, I'm just curious, what was the initial mass of the diquark, of the spectator diquark? And then when you let it run or turned it into a spectral function, where was it peaked? Like how much did it change?
Yeah, that's a good question. I don't know off the top of my head.
Okay.
But because in a way, yeah, because in a way, a lot of that information kind of gets lost because it's integrated over, right? So yeah, I don't know the value right off the top of my head what it was. Okay. Yeah, I can tell you that the final value ended up being, I think it being peaked at like 0.6. Yeah.
So 600 MeV. Yeah.
Yeah.
Interesting. I like that value. And I'll tell you why tomorrow.
Awesome.
Anyway, okay. So if there are no more questions, Brendan, let's just, I'll thank you again very much for accepting our invitation. And I will stop the recording.